The universe was once smaller than a grain of dust. And yet, within that impossibly tiny point, every star, every atom, every heartbeat of time was waiting to unfold. In the first second after the Big Bang, physics behaved like nothing we know. A reality made of heat and pressure beyond imagination, where space grew faster than light and time itself was still learning to move. Tonight, we drift into those earliest instants, into the moment when the universe was newborn, when temperature shaped matter, when forces fractured from unity, and when space began stretching toward infinity. Everything you have ever seen or touched was forged in the quiet chaos of that first second. Before we begin, if this quiet journey brings you even a moment of peace, I'm deeply grateful you're here. A gentle like or a soft tap on subscribe helps this little corner of calm science continue glowing in the dark. Now, we drift into Part 1. Part 1. A universe. Too hot for atoms. In the earliest fraction of a second, the universe was a storm of pure energy, far too hot for matter to exist. There were no atoms, no protons, not even light as we understand it. Only a blazing sea of particles flickering in and out of existence faster than thought. Space itself was still molten, expanding with silent urgency. At that moment, the universe was about 10 trillion degrees, a temperature so extreme that any structure, even the simplest, would instantly tear apart. You could not have held an atom in your hand then, because atoms were not yet allowed. The cosmos was ruled by one truth: energy mattered more than matter. And in such heat, even energy struggled to decide what it wanted to become. If you could somehow float in that first instant, though no you or floating or instant truly existed, you would find yourself in a place where physics was still being written. Particles popped into being and vanished again, not as objects, but as possibilities. You would not see light because photons could not travel freely. Instead, their paths would twist and break in a flash, absorbed by the dense, roiling chaos around them. Deep inside that chaos, time had barely begun. And yet, everything that would one day define the universe was being set into place. Its future galaxies, its stars, its elements, and every quiet world where life might one day breathe. All of it was encoded in the way that energy churned in those early heartbeats of the cosmos. Even the idea of heat becomes strange here. Heat on Earth means random motion, molecules vibrating rapidly. But this was not molecules, it was not even atoms. This was motion written into the smallest possible places. A temperature made of fundamental particles moving at near light speed, colliding, splitting, and merging faster than any clock can measure. And yet, beneath the chaos, something orderly was forming. As the universe expanded, it cooled. Not like ice cooling in a room, but like a deep breath spreading into emptiness. Every fraction of time meant a larger universe and a slightly calmer one. The violent collisions remained, but the average temperature stepped lower, one unimaginable degree at a time. With cooling came transformation. In the first trillionth of a second, forces that are now separate were still fused together. Gravity did not yet behave differently from the strong nuclear force. Electricity and magnetism had not emerged from their shared identity. Physics, the rules we rely on, were still deciding who they would be. And slowly, as the heat ebbed, unity broke. Gravity stepped away first, defining the shape of space and the pull between things. The strong force separated next, destined to hold atomic nuclei together. Later came the weak force and electromagnetism, which would control how particles decay and how light shines. The greatest symmetry ever known fractured into the laws we study today. The universe did not shatter when this happened. Instead, it organized. What had been a single storm of energy now had boundaries, behaviors, patterns. The cosmos was learning structure. The strange brilliance of that time was not in the heat, but in the moment of cooling. Because in cooling, energy could finally rest long enough to become matter. Quarks, the first building blocks, began to linger just a little longer before dissolving. They danced in pairs and trios, binding together with a strength that even the heat could no longer fully undo. In that fragile balance, the first hints of protons and neutrons emerged. but they were not stable yet. The temperature was still too high. Collisions still tore them apart as fast as they formed. Imagine a sandcastle built on a shore where waves strike every second. Each structure exists for a moment, then returns to the sea. That was the universe now. Structure in flashes, destruction in the next heartbeat. But the pattern was shifting. The waves were slowly calming. Even though atoms were not possible, even though no light could escape, the universe was preparing for the first promises of order. If you were there would be no sound. Sound needs air to carry it, something that can compress and stretch. Here, nothing like that existed. So instead, everything happened in silence. A silence made not of peace, but of pure potential. As the universe continued to double and double in size, pressures eased, energy thinned, the plasma became just a little less dense, and structure, long forbidden, began to find protection in the cooling dark. In this growing space, one rule emerged again and again. Motion creates stability. Particles spun, collided, and fused, driven by the lingering echo of cosmic inflation. Momentum carried them into patterns that would echo forever in the atoms of stars, in the molecules of life, even in your own blood. The universe was not trying to create life, it was simply obeying its laws. And those laws, newly born, would naturally lead to complexity. There were still no stars overhead. There was no overhead at all. There were no directions, no up or down, only expansion. But if we observed this time from outside, if such a viewpoint existed, we might describe it like a sunrise. The blinding, shapeless brilliance of the beginning was softening. What was once impossible was now merely unlikely. A universe that had once been nothing but energy was now preparing to give birth to matter that could last. Something profound was happening without witness and without sound. The future was beginning to survive. Tiny fluctuations in density, once random, became seeds of structure. Places where gravity would someday gather matter into galactic clusters. Minuscule imperfections that would grow into everything visible in the sky. And even as everything rushed outward, the memory of that heat remained inside every particle. It would linger across billions of years. It would glow in microwave radiation that still fills the sky, a relic of that scorching birth, a quiet reminder that we come from fire. As the universe cooled below 1 billion degrees, just a fraction of a second old, matter and energy entered a delicate negotiation. Most particles annihilated with their opposites, matter with antimatter. Their collisions turned back into light that could still not travel, trapped in the cosmic plasma. But not all vanished. A tiny excess, 1 in 1 billion, survived. That tiny fraction is everything, every planet, every star, every living cell, every moment you have ever known, all descended from the particles that endured when the flames finally allowed permanence. In the silence of that first second, the universe was still too young to shine, but the blueprint of light, of stars that would one day ignite, was already written. And as we continue this quiet journey, one question rises gently from those first flashes of existence. How did the chaos of pure energy transform into the first true pieces of matter, the protons and neutrons that built the universe? Now, we drift into part 2. Part 2. When space expanded faster than light. Cosmic inflation began almost instantly, an expansion so rapid that distances doubled again and again in a tiny sliver of time. Galaxies that would one day be billions of light years apart were once neighbors, torn from each other by the universe's first silent acceleration. This moment, so brief it cannot truly be pictured, reshaped everything that would ever exist. Before inflation, the cosmos was smaller than a proton, a tiny patch of space shimmering with energy. Then, in far less than the blink of an eye, it expanded by a factor so large that numbers fail us. The entire observable universe, all 90 billion light-years of it, once fit inside a speck smaller than a single atom. And it didn't drift outward the way shrapnel does from an explosion. It stretched. Space itself. Inflated, dragging every point within it apart. No wind, no roar, no fire. just a perfectly silent, unstoppable expansion. The laws of physics allow objects to move through space slower than light, but space itself has no such limit. Einstein's speed limit applies only to motion in the universe, not to the growth of the universe itself. So in this phase, space expanded faster than light could ever hope to keep up. Distances grew faster than photons could cross them, sealing off regions from one another forever. Even today, some galaxies are being pulled away from us by this expansion faster than their light can travel back. We will never see them, never know they existed. They are written into the cosmos but erased from our view. If you could stand inside the early universe, though there was no ground to stand on, you would not notice the stretching. Space is not like a rubber sheet that can be felt beneath your feet. Instead, you would simply notice that everything around you was slipping away, every direction growing larger at once without any motion at all. Inflation did not just make the universe large, it made it smooth. Before inflation, random quantum fluctuations rippled through the fabric of everything, tiny variations in density and energy. When space stretched, those ripples stretched too, becoming the seeds of every galaxy, every cluster of stars, every cosmic structure that now paints the universe in patterns of light and silence. What was once unimaginably small, smaller than a trillionth of a meter, grew into a cosmic landscape. Hills and valleys of matter formed, invisible at first, waiting billions of years until stars lit the darkness and traced their shapes across the sky. Those tiny imperfections, amplified by inflation, became the great architecture of the cosmos. The galaxies you see tonight were once flickers of quantum foam. This idea that the largest structures in the universe grew from events smaller than anything we can measure is one of the most beautiful discoveries in modern science. Inflation explains another quiet mystery: why the universe appears the same everywhere we look. Light takes time to travel. So when the universe is observed across billions of light years, we see faraway regions that should never have had a chance to communicate, too distant for light to pass between them since the Big Bang. Yet they are nearly identical in temperature and density. How did they synchronize? How did they decide to behave the same way? Inflation answers. Those regions were once side by side, touching, connected, before space stretched them apart faster than light could react. They began in the same moment, in the same place. Their uniformity is not a coincidence, it is a memory, a cosmic whisper carried across eternity. But inflation did more than smooth the universe, it flattened it. If you fire two rays perfectly parallel across a sphere, they eventually meet. But across the universe, they do not. Measurements show that space is almost exactly flat. Geometry obeys the same rules billions of light years away as it does here. Inflation stretched any initial curvature so wide that it became indistinguishable from flatness. A curved cosmos was ironed into simplicity. Even the deepest silence of space carries traces of inflation's work. The cosmic microwave background, the faint afterglow of the Big Bang, still bears the imprint of those stretched quantum fluctuations. The pattern is subtle, a map of temperature variations just one part in 100,000. Yet, inside that pattern lies a perfect match to inflation's predictions. Satellites like NASA's WMAP and ESA's Planck mission have measured this pattern with exquisite precision. The whispers of that violent growth are now encoded in the gentle static that fills the universe. And still, inflation remains one of the most mysterious stages of reality. We do not know exactly what caused it. Perhaps it was driven by a field, a form of energy woven into the fabric of space. Perhaps it was a phase transition, the universe shifting states like water freezing into ice. Perhaps it hints at deeper dimensions beyond our perception. Some theories suggest inflation never truly ended. That while our region slowed down and became a universe filled with stars, other regions continued to expand into infinity, creating countless disconnected universes. A multiverse, not of science fiction, but of mathematics and cosmology. An endless cosmic foam, each bubble a universe with its own laws and stories. We live in one bubble, surrounded by countless others we will never see. To us, the night sky feels infinite. To the deeper truth, it may be just one world among many. And yet, for all its scale, inflation was not chaos. It was a doorway to order. The furious expansion eventually slowed. The universe cooled. Forces separated into those we know: gravity, electromagnetism, the nuclear interactions. Space stopped racing and settled into a calmer, gentler expansion. The frantic birth gave way to a long childhood. Cosmic inflation ended, but expansion continued. Slower now, quiet now. What began in violence would eventually welcome stars, planets, oceans, and the possibility of observers like you. If inflation had lasted longer, matter might never have been dense enough to gather into galaxies. If it had lasted less, the universe might have collapsed back into silence before anything could form. It was a moment balanced on a razor's edge, and somehow the balance held. All you have ever loved or wondered about exists because of that brief, perfect eruption, because space itself chose to grow faster than light could chase it, because in that instant, the universe decided there would be room for everything. Now, as we drift forward through time, one gentle question remains. When space finally slowed, what did that cooling allow the universe to create? The answer lies in the first true building blocks, the protons and neutrons that would assemble the future. So we continue into Part 3. Part 3. The birth of forces, unity breaking. At the beginning, there was only one force, a unified field holding all physics together. But as space cooled ever so slightly, this unity fractured. Gravity stepped apart, then the strong nuclear force, then the weak and electromagnetic. The laws of nature began to specialize, shaping everything that would come after. In that earliest moment, the universe didn't yet know the difference between attraction and repulsion, between light and matter, between the forces that bind and the forces that break. Everything was folded into one elegant rule, one perfect symmetry, a single fabric of physical law that guided every flicker of energy. But perfection can be fragile, and as the universe expanded and cooled, that symmetry could no longer hold. The first force to separate was gravity. This gentle shaper of orbits and oceans was once the strongest presence of all, fused with the other forces into a single unified entity. But cooling changed the rules. Gravity stepped away, defining how space curves, how matter clumps, how the universe grows its structure. What once bound everything together now created distance, separation, motion. Gravity became the quiet architect of the cosmos. Next, another break, one that would decide how matter could survive the storm of creation. The strong nuclear force emerged, unimaginably powerful at extremely short distances. It was the force destined to hold the centers of atoms together. Though gravity would control the expansion of the universe, the strong force would define the very backbone of matter itself. It grabbed quarks, the tiny fragments that had begun to appear, and pulled them into tight triplets, refusing to let go. Even today, quarks cannot be isolated. They are imprisoned inside protons and neutrons, bound by the strong force's impossible strength. It is the most powerful force in the universe, but only inside the smallest spaces. Soon after, the symmetry broke again. The weak nuclear force separated from the force of light. The electromagnetic and weak forces had once been one and the same. Their union gave the early universe a graceful structure, but cooling forced another split. The weak force is subtle, responsible for radioactive decay, and one of the earliest alchemical transformations in the cosmos, the turning of protons into neutrons and neutrons into protons. Without that quiet exchange, the recipe of elements would have failed before it began. And finally, the electromagnetic force stood alone, the sculptor of atoms, the painter of light, the reason why electrons dance around nuclei instead of falling into them. It became the force of everyday experience, shaping everything you see, touch, and sense. Gravity governs the stars. Electromagnetism governs your heartbeat. Each separation, each fracture in symmetry brought complexity. And with complexity came possibility. We often imagine breaking as destruction, but here, breaking was creation. Like a prism splitting white light into a rainbow, unity breaking created diversity. Once all forces were equal. Then each claimed its role, its scale, its influence over the universe's unfolding story. The physics that today feels stable and certain, the steady pull of gravity, the sparks when electricity flows, the fusion deep in stars, all of these are products of this early transformation. If the splits had happened differently, if the forces had divided with just slightly different strengths or timing, the universe would have been unrecognizable. Matter might never have formed, stars might never have ignited, life might have remained impossible forever. And yet, the balance was perfect. Perfect enough for everything that followed. It is a strange truth. The universe was built on a series of accidents that were not accidents at all. Physics chose a path, and we are the distant result. During this time, the universe was still incredibly hot, trillions of degrees, so hot that the newly born forces acted with fierce energy. Gravity pulled, the strong force forged, the weak force transformed, electromagnetism illuminated. Four siblings, once indistinguishable, now forming the entire language of nature. The universe's earliest moments are like a symphony. In the opening note, all instruments played the same tone, a single voice. Then the harmony began. One instrument after another stepped forward, adding complexity, depth, and structure. Symmetry breaking wasn't a flaw. It was the beginning of music. Even now, physicists search for the memory of that lost unity. They build colliders that send particles crashing together at near light speed, trying to recreate the temperatures of the first moments, hoping to glimpse the forces reconnecting as one. We call that dream the theory of everything, a single equation that explains every motion in the cosmos, every atom, every galaxy, every moment of time. Gravity has been the most difficult piece to fit into that puzzle. It refuses to merge cleanly with quantum mechanics, as if still proud of being the first to walk away. Some theorists suspect there may be hidden forces we have not yet discovered, forces that acted in those first fractions of a second, but faded as the universe cooled. If inflation, the great expansion, was driven by a field or a force, we have not yet found it. The universe has not revealed all of its secrets, yet one truth is clear. From this moment of symmetry breaking, a new era began. Particles had roles, forces had purpose, physics had rules that would endure. What had been a chaotic ocean of pure energy was now slowly becoming a place where matter could exist. Quarks and gluons, the fragments of everything, were finding stability inside the strong force's embrace. Gravity was beginning to guide gas toward the seeds of future galaxies. The electromagnetic force would one day let atoms form in perfect orbits, and the weak force would help shape the elements of stars and life. It was still far too early for atoms, far too early for stars or planets or anything that glowed in the darkness. But the framework was set. The universe had written its laws. Its physics was no longer inventing itself. It was following its script. And that script would lead from the smallest particles to the largest structures, to the quiet places where a mind might one day wonder how it all began. Yet, even with the forces now distinct, matter itself was not ready. Particles struggled to hold together under the crushing heat. The early universe was still too bright, too hot, too young. So now, we move forward in time, to the moment when quarks finally join in a bond that the heat can no longer undo. A moment when stability arrives. A moment when the first building blocks of atoms take shape and endure. And that question guides us gently toward our next chapter. How did the universe take those new forces and use them to create the first pieces of matter that would last? Now, let us drift into Part 4. Part 4. Quarks, the first building blocks. Within a millionth of a second, the universe cooled just enough for its earliest ingredients to appear. Quarks, tiny fragments that would someday join into protons and neutrons, forming the atomic hearts of every star and planet. Before this moment, nothing solid could survive. Any structure that tried to form was immediately torn apart by the heat, like frost melting against a flame. But now, in this brief pause of cooling, the chaos softened just enough for matter to begin experimenting. Quarks are not like anything in the familiar world. They cannot be seen, even with the most powerful instruments humanity has built. They cannot be isolated or held in your hand. They exist only in groups, bound so tightly together that they never let go. They come in 6 varieties: up, down, charm, strange, top, bottom. Poetic names for particles smaller than imagination. Yet only 2 would shape the matter of everyday life. Up quarks, down quarks, these 2 simple kinds, combining in 3s, became the foundation of all visible creation. At this moment, quarks still roamed freely through a hot, dense medium known as the quark-gluon plasma. Think of it as a sea of particles so energetic that nothing had yet settled into form. Gluons, the carriers of the strong nuclear force, zipped between quarks, pulling and releasing, guiding their first attempts to bond. The strong force is relentless. It does not weaken as particles move apart. It grows stronger. A force that is weakest when quarks are together and strongest when they try to separate. Because of this, quarks are forever trapped in companionship. They cannot escape their groups. This rule, the rule that quarks must stick together, is the reason matter does not fall apart. It is the reason atoms can exist. It is the reason stars can burn. The universe was still hotter than the core of any star that would someday ignite. But even here, quarks were learning how to stay together longer than a moment. These early bonds were fragile, constantly breaking and reforming under the crushing heat. But every attempt taught the universe a new lesson in stability. Time was passing, although at a rate so strange, so compressed, that what would one day feel like a lifetime was only a breath. A millionth of a second, a heartbeat in creation. With each breath of cooling, the quarks lingered a little longer in their groups. Groups of 3 began to form with increasing confidence: baryons, the family that would include protons and neutrons. A proton, 2 up quarks and 1 down. A neutron, 2 down quarks and 1 up. 3 pieces, all held together by the strong force, like 3 dancers in a circle with hands forever locked. These were the first stable building blocks, not atoms, not elements, just the raw cores of what would become everything. Yet, stability was still precious and rare. The universe remained a furnace of unimaginable energy. Collisions were constant, violent, and unpredictable. A newly formed proton might exist for only the briefest instant before being smashed into pieces again. But progress was unstoppable. Cooling continued, even if barely noticeable. With every passing fraction of a second, quarks found it easier to stay bound. The cosmos was learning patience, learning the art of structure. If you were somehow able to perceive this era, if you could slow time enough to watch, you would witness a kind of cosmic metallurgy. Quarks forging themselves into the first particles of lasting significance, sparks of matter emerging again and again from the turbulence. Each success a step toward the world we know. As protons and neutrons became more numerous, a new balance began to emerge between matter and antimatter. For every proton, an antiproton existed. When they met, they annihilated, returning to pure energy. The universe was still locked in a war between creation and uncreation. For a long while, matter and antimatter destroyed each other almost perfectly. Almost. Somehow, for reasons not yet fully understood, matter gained a tiny advantage. For every billion particles that vanished together, one survived. That single survivor out of a billion was enough. Enough to build every star, every moon, every drop of water, every living cell. Enough to ensure that the universe would not fade back into pure radiation. The quarks that endured would one day form the atoms in your bones, the light inside distant galaxies, the dust that becomes planets. They are ancient beyond measurement, survivors of the very first battle in cosmic history. By the time 1/10,000th of a second had passed, the universe had changed irrevocably. The quark-gluon plasma had thinned. The strong force had done its job. Protons and neutrons were no longer rare visitors. They were residents, able to endure. These particles did not yet know that they would eventually fuse into hydrogen and helium, the first elements. They did not yet know that gravity would gather them into stars where nuclear fire would create the heavier elements of life. For now, they simply survived. And survival was enough. Matter was becoming real, not as a fleeting idea, but as a lasting presence. The orchestra of physics was beginning to play in harmony. Gravity would soon gather these particles together into clouds. Electromagnetism would shape the first atoms. The weak force would help matter transform into new forms of nuclei. The strong force had lit the first spark. From this point forward, the universe would never be the same. If the earliest instance were pure energy, a storm without structure, this moment marked the universe's first true memory. A record of what had happened so far, written into the particles that would carry that story forward. And even though everything would change, even though stars would rise and galaxies would bloom, the quarks inside those first protons and neutrons would remain the same quarks you are made of now. Inside every atom in your body, there are quarks nearly 14 billion years old, still locked in their eternal embrace, still dancing the same simple rhythm they learned when the universe took its first breath. The heat of creation lives inside you. The first stability still pulses through your bones. From chaos came structure, from flicker came form, from quarks came the beginning of everything. But these tiny triplets were only the first step. Now that they existed, they would need to gather, to fuse, to transform into the first atomic nuclei. And so we move forward to the moment when protons and neutrons truly begin to build the universe, one element at a time. Now we drift into Part 5. Part 5. A plasma ocean without light. Even once particles formed, photons, the particles of light, could not travel freely. They were instantly trapped, absorbed, and scattered in a dense fog of matter. The universe was brilliant but blind, glowing with light that had nowhere to go. Imagine an ocean where every droplet is glowing, radiant, luminous, full of energy, yet nothing can be seen beneath the surface because the water is too dense. That was the early universe, a blinding brilliance hidden inside a perfect fog. Light existed, but illumination did not. There were no beams, no shadows, no transparency, only a haze so thick that the very concept of sight would have been impossible. This early state was something physicists call an ionized plasma. Every proton was detached from its electron. The two could not stay together in such heat. Instead, they drifted apart, each carrying electric charge, free to interact with every photon that tried to move through space. Photons collided constantly, again and again and again, scattering off electrons with no path to escape. This cycle repeated trillions of times a second. Every attempt at a straight line was interrupted. Every journey was shortened into chaos. The universe glowed, but it did not shine. Even though the chaos was cooling, the temperature was still around billions of degrees, hotter than the cores of the brightest stars that would someday exist. This heat kept matter in a state of separation, preventing anything like a stable atom from forming. In these moments, the shape of the cosmos was set not by clarity, but by pressure. Light exerted force on matter. Matter pushed back. That balance, known as radiation pressure, kept the universe smooth and uniform for a long time. So while galaxies were not yet possible, the future galaxies were being planned in silence. If you could drift through the universe, then, without being instantly vaporized, you would find the environment strangely even. No stars, no planets, no voids or clusters. A perfectly balanced plasma filling every direction, everything everywhere, all at once. This uniformity may seem uneventful, but it was essential. Too much clumping too early, and gravity would collapse everything into black holes before stars could ignite. Too much smoothness forever, and nothing would ever gather together to shine. But the universe, through a delicate coincidence of density, gravity, and expansion, chose the middle path, a cosmic equilibrium. As time stretched on, the temperature continued to fall like a slow exhale. Protons and neutrons drifted close enough to sometimes hold together in fragile nuclei. Hydrogen and helium nuclei began to form. But electrons still resisted attachment. Their wild motion from the heat prevented any lasting union. The universe remained a plasma, the electrons still free, their buzzing chaos still scattering every photon. In this era, light was a prisoner, not in darkness, but in confinement. Everywhere glowed with the same unbearable brilliance. Yet the cosmos was black. There was no medium clear enough for photons to travel at the speed they desired. No line of sight could stretch more than a fraction of a millimeter. Light and matter were locked in a frantic dance, neither able to step aside. As the universe expanded, the distances between particles increased. Collisions became a little less frequent. Heat dropped degree by degree, though still far hotter than any earthly furnace. Roughly 3 minutes after the Big Bang, a remarkable transformation began to settle. The first elements appeared: hydrogen, helium, a trace of lithium, not full atoms yet, only their nuclei, but the foundation was in place. The recipe that would one day cook stars had its ingredients ready. And still, no light escaped. It would take hundreds of thousands of years for space to cool enough that electrons would finally calm down and attach to nuclei, forming true neutral atoms. Only then would photons be released from their prison. But that moment was still unimaginably far in the future. For now, a glowing haze covered everything. It is a strange thought. The universe did not begin dark. Darkness came later. When the plasma finally thinned and light was released, photons traveled freely for the first time. But before that release, the universe was too bright for sight and too blocked for illumination. Brightness without light, glow without vision, radiance without revelation. We sometimes picture the universe growing into brilliance, but the truth is the opposite. It began brilliant, then faded into night. Only much later did the stars reintroduce light that could be seen. The plasma ocean was a world between worlds, too young for structure, too energetic for peace. Yet inside this chaos, order was waiting. Minute variations in density, created during cosmic inflation, were now taking on meaning. In places where matter was slightly denser, gravity tugged harder, gathering particles just a little more than the surrounding space. These tiny differences, just fractions of a percent, would one day become galaxies, stars, solar systems, and the cradle of life. Every cluster of galaxies today can trace its origins to those early ripples in the plasma. The fog was not featureless. It held the blueprint of everything to come, and the photons, trapped and struggling, were writing that blueprint for us to one day discover. Because as they collided and scattered, they recorded temperature variations and density maps. They imprinted the state of the universe onto themselves. When the time finally came for light to break free, the moment known as recombination, those photons fled across space untouched. They stretched with the universe's expansion, cooling into microwaves, becoming what we now observe as the cosmic microwave background, the oldest light in the universe. It is a glowing whisper from a time before stars, carrying a perfect snapshot of the plasma ocean's final moments. A message across 13.8 billion years, a photograph of childhood taped to the sky. But here, in Part 5, we remain in the era before that release, before freedom, before sight. The universe was still too young to reveal its face. Light was energy without expression. Matter was structure without form. Time was motion without story. And yet, in that glowing blindness, the pieces of the universe were beginning to know who they would become. Electrons would soon fall into orbit around nuclei. Atoms would take their first shape. Gravity would gather clouds into the first stars. And with starlight, darkness would end. The haze would thin. The plasma would cool. The universe would finally learn to shine. But to reach that destiny, the young cosmos had to endure its long, bright blindness, a fog that hid the future while preparing the way. As this dazzling ocean of plasma continued to cool and expand, one question gently emerged. When would the darkness finally arrive? When would the universe, bright but unsighted, give birth to light that could be seen? The answer lies in the next chapter of this quiet journey. Now, we drift onward into Part 6. Part 6, Time Learns to Flow. In these first moments, the arrow of time emerged from the imbalance between order and chaos. Energy moved, Heat flowed, entropy rose. From that one direction, from hot to cold, the universe gained its sense of before and after. Before the Big Bang, if we can even say before, time did not behave the way it does now. There was no ticking of moments, no unfolding of events. The universe was not yet a place where causes led to effects. It was a singular state, all possibilities, no direction. But the instant expansion began, something subtle and profound changed. The universe was no longer in perfect balance. Heat streamed outward, matter clumped here and thinned there, and every tiny shift created a path forward. With motion and difference came sequence. With sequence came time. Physicists describe this direction as the arrow of time, the simple idea that entropy increases, not chaos in the everyday sense, but a gradual spread of energy into more and more possible arrangements. High concentration flows into low. Heat leaks from the hotter place to the colder one. This is why a glass shatters but the shards never leap back into a glass, why smoke disperses but never regathers into a matchstick, why you grow older and not younger. Time is not a clock. It is the preference of the universe for disorder over order. In the beginning, the cosmos was extraordinarily ordered. All energy was packed into a tiny space, perfectly uniform and impossibly dense. There were almost no places for things to move, no room for anything to unfold. But once the universe expanded, room appeared. Suddenly, everything could change. And once change was possible, time was inevitable. The heat from the first instant radiated outward into newly formed space. Expansion cooled the universe just enough to allow quarks to form, then protons and neutrons, and eventually atoms. In every step, energy dispersed a little more. Entropy was rising, time was flowing. It is astonishing to think that the reason you can remember yesterday but not tomorrow is because the universe started hot and became cooler. If expansion had not created an imbalance, if everything remained perfectly still and uniform, there would be no memory, no thought, no life. A universe without entropy change would be a universe without story. If we imagine diving down to the smallest scales of the early cosmos, we would find time itself behaving strangely. Quantum mechanics tells us that on the tiniest scales, events do not follow smooth paths. Instead, they jitter and flicker with uncertainty. At that level, time is not continuous. It comes in tiny, indivisible moments, as if reality blinks into existence one frame at a time. But on the vast scale of the early universe, where countless particles moved in unison, these quantum jitters averaged into a smooth river. Time as we know it. Even as photons were trapped in the plasma fog, even as the universe existed in blind brilliance, the arrow of time pointed forward. More states became possible, more structure could form. At every scale, the cosmos embraced transformation. Energy flowed outward, driven not by choice, but by the simple law that things spread. Gravity quietly began to gather matter into gentle ripples, places where stars would someday ignite. Atoms were not even possible yet, but the future was already being arranged. Time is not something the universe carries. Time is something the universe does. The direction of time is stitched into every physical law. The strong nuclear force binds quarks together and releases energy into motion. The weak force allows particles to transform and decay. Electromagnetism arranges electrons around nuclei. Gravity shapes the paths of planets and galaxies. Each of these forces enforces a type of change, a push toward the next moment. Even in this early plasma, before any star existed, particles decayed and collided, bonded and separated. Every event erased the possibility of the state before it and opened a new set of possibilities ahead. This is the essence of time. The universe cannot return to a perfect copy of what it was. Some have wondered, if the universe began in perfect symmetry, why didn't it stay symmetrical forever? The answer lies in a quiet feature hidden in physics: spontaneous symmetry breaking. Like a perfectly balanced pencil standing upright, the early universe's symmetry was delicate. The tiniest fluctuation determined how the pencil fell, which direction became down. When the forces separated, the universe chose a direction for time, forward. This breaking of balance set the cosmic story in motion. As the universe grew larger, the scale of time grew with it. Moments that once passed in unimaginably quick flashes began to stretch. Processes took longer. The cooling slowed. And with each slowing, the unfolding of events became more complex. Entropy was still rising, but now it did so in ways that built patterns rather than destroying them, a paradox at the heart of existence. Order emerged from the push toward disorder. Simple hydrogen and helium nuclei would one day gather into stars. Stars would fuse heavier elements. Those elements would form planets. Planets would form oceans. Oceans would form chemistry. Chemistry would form life. Even now, every living thing is an island of fleeting order carved out of an ocean of rising entropy. Life does not fight the arrow of time. It surfs it. And you, sitting here, breathing, listening, are a direct continuation of that first direction the universe chose. The arrow of time flows through your thoughts. Every memory is a trace of entropy growing. Every heartbeat is a moment when energy flows from high to low. Every future holds more possibilities than the past. The universe has been following that path for billions of years. But in this early era, time was still learning its pace. Events happened quickly, but not yet richly. The plasma glowed, but did not yet radiate freely. There were no days, no nights, no cycles, only a smooth flow from hot to less hot, from dense to less dense, from the simple to the slightly more complex. Time's pulse was still young, still bright, still made of fire. As entropy continued its steady climb, the universe approached a remarkable transition. The plasma would eventually cool enough for electrons to settle into orbits around nuclei. Then, only then, would photons be released into freedom. The first true moment of sight. The first moment where space became transparent, the birth of a visible universe. Time had been preparing the stage for that moment from its first breath. Entropy drove change. Change built structure. Structure allowed light to travel. And when that light finally escaped, it carried the memory of the early universe with it, a snapshot etched across the sky that we still observe today as the cosmic microwave background. But before we reach that clarity, we remain here, in a universe still glowing, still blind, still young. Time has direction now, but the future remains entirely dark. So we follow that arrow forward, toward the moment when the universe takes its first visible form. As we drift on, a quiet question carries us forward. What happens when time slows enough for atoms to finally hold together, and when space becomes clear enough for the first light to truly shine? Now, we move gently into Part 7. Part 7. The first second. Protons take shape. At precisely 1 second after the Big Bang, something remarkable stabilized. Quarks locked together, forming the first protons and neutrons. What seems simple now was once revolutionary. The universe had created something that could last. Until now, the newborn cosmos had been a place where structure dissolved faster than it formed. Every attempt at permanence was shattered by unimaginable heat. But at this moment, 1 second into existence, the universe crossed a quiet threshold. Temperature dropped just enough for the strong nuclear force to finally hold its creations together. From that stability came the first true pieces of matter, not atoms yet, not elements, but the central cores that would one day shape every star, every planet, and every living thing. In those early seconds, protons and neutrons did not float alone. They were swallowed in a vast sea of energy, a plasma so dense that collisions were constant. Neutrinos streamed through this chaos, already beginning to slip into the dark, escaping interactions entirely. They were the first messengers of change, carrying information about those early moments into the distant future. Protons and neutrons, however, had work to do. They needed to find each other. They needed to build something more. The first second was a race between formation and annihilation. Matter was almost perfectly matched by antimatter, and every collision between the two erased both from existence in a flash of light. For every particle that survived, a twin vanished in radiant defeat. Yet, matter won by the smallest margin imaginable. 1 extra proton for every billion that faded. That tiny imbalance, that 1 in a billion statistical miracle, guaranteed a future where something could exist rather than everything dissolving back into light. It is humbling to realize everything in the universe is built from the leftovers of annihilation. In this 1-second mark, the average temperature was around 10 billion degrees, still hostile beyond imagination, yet tame enough for bonds to endure. Neutrons and protons moved rapidly, banging into each other like flint and steel in the inflation-shaped void, occasionally sticking together to form fragile beginnings of atomic nuclei. For brief moments, deuterium, a combination of one proton and one neutron, appeared, only to be pulled apart again by energetic photons. The universe was trying to build, yet the conditions still fought against it. It was as if the cosmos had learned the idea of permanence, but had not yet mastered its technique. Even in this turbulence, the future was quietly unfolding. Gravity was beginning its long task, gently slowing the expansion, not enough to stop it, but enough to leave fingerprints on the motion of matter. The curvature of space and the ratios of force were already determining the shape of everything to come. During this second, the weak nuclear force also stamped its influence on the universe. It dictated the delicate balance between protons and neutrons. Neutrons decay if left alone, but here, they constantly exchanged identity with protons, flipping between forms in a dance driven by thermal collisions. The ratio of protons to neutrons settled into a stable pattern, about 7 protons for every 6 neutrons. That ratio will become essential, because when nuclear fusion truly begins minutes later, that proportion will decide how much helium the universe forms, influencing the birth of stars billions of years down the line. A simple ratio set in 1 second guides the chemistry of galaxies. The first second also marked the end of one era and the beginning of another. Up to now, the universe was dominated by radiation, pure energy directing the fate of matter. But from this point forward, matter slowly began to take control. The destiny of the cosmos shifted from light to substance. The moment had another astonishing consequence. Time became slow enough to recognize. Events no longer flashed in and out before processes could complete. A second became meaningful, a measurable pause in the breathing of cosmic evolution. Imagine the scene. A universe the size of our solar system, glowing everywhere. No stars, no planets, only free protons and neutrons. Neutrinos racing outward, carrying early whispers of temperature. Light, constantly colliding, unable to escape gravity, beginning to sculpt invisible patterns. It was still a place without sound. No air, no waves to carry vibration, but the silence held potential. We often imagine the Big Bang as an explosion that happened long ago. But in this moment, the universe isn't exploding. It's transitioning, transforming from a violent fireball into the quiet architect of galaxies. Inside every proton that stabilized in that first second lies a history billions of years long. Those protons did not decay. They persisted. Many of them are drifting through you right now, relics of that ancient forging. The hydrogen in your blood was once a scatter of particles trying to survive the first second. The atoms in distant stars were once frantic quarks learning to stay together. Every piece of matter that has ever existed descends from that moment, and as the proton formed, so did the possibility of a future universe. The laws that emerged in earlier moments, gravity, the strong and weak nuclear forces, electromagnetism, were now working in concert. They had roles, they had stability, they had direction. In the first second, the universe discovered how to build. This calm, profound shift is easy to overlook because it feels so simple. Protons and neutrons are familiar, ordinary. They form the heart of every atom, so every day we barely think of them. But simplicity is the greatest achievement of nature. The universe built complexity from the smallest, strongest pieces, and this was just the beginning. A foundation still needed walls. Those walls would someday be atoms. Those atoms would someday be stars. Those stars would someday create worlds and light and life. But none of it could begin until the universe took this quiet step. 1 second in, protons enduring, matter existing. As we drift forward through the cosmic timeline, a new question unfolds. With the first building block stable, How did the universe begin assembling a chemistry that could ignite the stars themselves? Our journey now moves into the era when matter begins to form rules and the cosmos takes its first deep breath. Now we drift onward into Part 8. Part 8. Neutrinos slip into the dark. Some particles escape the chaos entirely. Neutrinos, ghost-like and nearly massless, stopped interacting with the newborn universe and slipped away into infinite darkness. Even today, trillions stream through your body every second, whispering a story from the very beginning. In the first seconds of the cosmos, every particle was trapped in constant collisions. Nothing could travel far without being pulled back into the swirl of heat and density. But the neutrino, elusive and silent, found a loophole. It interacts so weakly with matter that it can drift straight through stars, through planets, and through every cell in your body without pausing, without slowing, without leaving a trace. When the universe was only 1 second old, the temperature fell just enough that neutrinos no longer collided frequently with other particles. They simply decoupled, slipping out of the cosmic crowd and beginning their long journey outward. The glow of the early universe remained trapped, photons still scattering in the fog of charged particles. But neutrinos were free. They were the first messengers of time, carrying information from that era into eternity. If photons are the storytellers of the visible universe, neutrinos are the witnesses of everything that remained unseen. In that early silence, the neutrinos fled the heat, racing outward at almost the speed of light. They filled the growing universe like a gentle wind that has never stopped blowing. Scientists call this invisible sea the cosmic neutrino background, a quiet ocean still flowing through the cosmos today. Those first travelers are still here. They pass through worlds that did not exist when they began their journey. They pass through you, billions each second, and never say a word. To understand a neutrino is to understand minimalism in physics. It has almost no mass, no electric charge, no presence to the electromagnetic senses. It does not shine. It does not gather. It does not build. And yet, neutrinos matter because they do not interact. Their silence protects memory. They preserve the state of the universe as it was in its earliest instant. If we could detect them clearly, if we could hear their whisper, we would gain the ability to look back farther than any telescope can reach. Before photons were free, before the cosmos turned transparent, neutrinos left their imprint. Even though they are almost impossible to catch, we have managed to glimpse them. Deep beneath mountains and inside ice and in vast underground chambers filled with still water, scientists wait for a single telltale flash, a rare interaction, a neutrino brushing reality just enough to light up a sensor. These moments are celebrated because each one is a message from the universe itself, a particle that has traveled unchanged across billions of years. Neutrinos are often described as ghost particles, but that metaphor is incomplete. Ghosts haunt the past. Neutrinos carry the past. They are the oldest travelers we can detect, the long-distance runners of reality. At the moment of their escape, about 1 second after the Big Bang, other transformations were also taking place. Protons and neutrons had just stabilized. The weak force's influence began to fade. The balance between the elements of matter was set. Neutrinos had helped shape that balance, influencing how many neutrons survived by subtly mediating the conversions between protons and neutrons. When they slipped away, the ratio froze, a perfect setup for forming hydrogen and helium minutes later. Their departure was like a curtain falling on the first act of creation. What remained inside the cosmic furnace would be left to the strong and electromagnetic forces, the builders. Gravity would lay the foundation for structure. But neutrinos had already played their quiet role and left the stage. They were never meant to shape the visible universe. They were meant to witness it. Imagine if we could harness their memory. Every neutrino that passes through Earth once traveled through the earliest plasma. Everyone contains a trace of the temperature, the density, the birth conditions of matter itself. They are like ancient postcards from a time when space was too dense for light to see. We cannot read them yet, but we know the message is there. For nearly 14 billion years, these particles have been gliding through everything the universe has created, through the first stars, the first galaxies, the first oceans, the first breath of every living organism. And because they interact so rarely, they arrive largely unchanged, unaffected, unaged. In the deep history of the cosmos, neutrinos mark the first moment when something escaped, the first moment when a particle could leave a region and never be pulled back again. Freedom began with them. Even now, trillions pass through your body each second, yet you do not feel them. Your atoms do not notice. No receptor reaches out to catch them. You only exist because they left, because their silence allowed matter to cool, allowed atoms to form, allowed the universe to slow and shape itself into stars and worlds. In a way, life depends on what the universe was able to let go of. The photons remained prisoners for hundreds of thousands of years. Matter stayed locked in a plasma haze, but neutrinos walked away untouched into a future that had not yet been written. Their decoupling marks a pivot in the cosmic story, from creation to construction. The heat that once powered every change began to settle. The furious collisions began to wane. The universe that had been nothing but a furnace of energy was becoming a place where influence could weaken and motion could endure. The cosmos had grown large enough for distance to matter, large enough for darkness to exist. With the neutrinos gone, the universe became a little quieter, a little more stable, a little more ready for the next transformation. These early moments remind us that not everything that shapes the universe leaves a visible trace. Some of the most important actors are those who exit the stage unnoticed. The particles that do not collide are just as important as those that fuse. Absence is as powerful as presence. Now, as the universe drifted into its second, then its third, the coming minutes would bring a remarkable transition: nuclear alchemy. Protons and neutrons would begin to fuse, creating the first true elements that would endure for billions of years. The universe was preparing to write its first chemistry. But before those elements take their place in the cosmic story, we honor the silent witnesses who made their formation possible. Neutrinos, free in the dark, messengers from the first heartbeat of time. And now, as we follow their quiet path forward, a gentle question emerges. What happens when the universe finally cools enough for matter to build something new, not just cores, but atoms that can shine? We drift now toward that moment. Part 9 awaits. Part 9. Gravity begins its work. Once matter existed, gravity, the architect of structure, began its slow and quiet labor. Invisible and gentle, it started pulling matter together, planting the seeds for stars that would not shine for hundreds of millions of years. Gravity is the most subtle of forces. It is weaker than the push of a magnet, weaker than the flicker of light, weaker than the nuclear forces that bind atoms and break them apart. Yet over the vastness of space and the fullness of time, it is gravity that shapes destiny. In the beginning, the universe was almost perfectly smooth, a uniform sea of plasma, all particles nearly evenly distributed. Too smooth for stars, too smooth for galaxies, too smooth for worlds where life might one day wonder how it all began. But almost was enough. Tiny imperfections left behind by cosmic inflation, slight variations in density, gave gravity something to work with. In places where matter was just a little bit denser, gravity pulled a little bit harder. These regions became gravitational wells, places where particles lingered slightly longer, slowing down, gathering. A quiet chain reaction began. More matter meant more gravity meant more matter. The early universe was still hot, still glowing, still fluid. But the seeds of structure were beginning to sprout, completely invisible to the eye, yet increasingly powerful. You can imagine the early universe as a great ocean after a storm. Waves settle, small ripples remain, and those ripples, left untouched, begin forming patterns. Gravity was the calm after the storm, and it used those ripples as guides. This was the age when gravity quietly claimed the future. Every star that would ignite, every black hole that would form, every spiral galaxy that would stretch its arms across eternity, all began as a whisper in these first patterns. While other forces worked quickly, forging quarks into protons, trapping photons in the bright haze, gravity remained patient. It never rushed. It didn't need to. Time favored gravity. Expansion slowed, matter cooled, and gravity's influence grew. As more protons and neutrons appeared, the balance shifted in gravity's favor. The universe was expanding, but expansion could not erase the pull of matter entirely. The deeper the gravitational wells became, the more matter sank into them. These wells, barely noticeable at first, are now the great clusters of galaxies, the brightest, superclusters, the threads of the cosmic web stretching across billions of light years. Gravity draws maps that only become visible after ages of darkness. In these early moments, space was still filled with plasma. Electrons roamed freely, preventing atoms from forming. Photons still ricocheted endlessly. Yet the future geometry of the universe was taking shape beneath that blinding haze, like mountains growing beneath clouds. This time, between 1 second and a few minutes old, saw the first nuclear alchemy begin. Gravity had created conditions where protons and neutrons could collide and stick together briefly, forming deuterium, helium nuclei, and a trace of lithium. This process, called Big Bang nucleosynthesis, set the elemental composition of the universe: about 75% hydrogen, about 25% helium, less than 0.01% everything else. Gravity had provided the canvas on which chemistry would one day paint the world. These simple elements would become the fuel for stars, the fires that would light the cosmic night after its long darkness. But that ignition was still unimaginably far in the future. Gravity had planted the seeds, but they needed time to grow. Hundreds of millions of years. To us, such a span dwarfs comprehension. To gravity, it was only a breath. As the universe continued to expand, the plasma thinned. Collisions became less intense. Regions with slightly more matter grew denser still. Already a cosmic network was forming, a web of matter tracing the faint scars inflation had left behind. Dark matter, mysterious, invisible, and numerous, played a crucial role. It does not interact with light, does not form atoms, does not shine, but it responds to gravity, and in doing so, it amplified the gathering of normal matter. Dark matter built the scaffolding. Ordinary matter followed. Gravity worked in partnership with the unseen. Eventually, gravity would draw matter into great swirling clouds so massive that their centers would collapse under their own weight. Hydrogen atoms would smash together, releasing energy and forging new elements. Stars would finally ignite. But we are still far from that moment. We are tracing gravity's early footsteps, long before the first starlight found its way into darkness. In these ages, time was marked only by temperature falling. A second passed, protons stabilized. A minute passed, nuclei formed. Tens of thousands of years passed. Matter began to dominate over radiation. Hundreds of thousands of years passed. Atoms finally appeared. Millions of years passed. Gravity sculpted the first clouds. Nothing visible was happening, and yet everything meaningful was. Gravity's genius lies not in sudden change, but in unwavering direction. It is the force of patience, of inevitability, of slow creation that becomes overwhelming in scale. Today, gravity is the reason the Earth holds you close. It is the reason stars burn, the reason galaxies spin, the reason the night sky exists at all. It is also the reason we can look back into time. Because the structures gravity built, clusters, galaxies, stars, become markers that tell us how space has stretched across billions of years. The cosmic web, now visible in telescopes, is gravity's great artwork, lines and nodes of structure spanning across the entire universe. Each connection began in these silent moments. There is something deeply poetic about a force so weak that you can overcome it with a single leap, yet so strong that it binds galaxy to galaxy across infinite distances. Gravity wins not with power, but with persistence. As the universe cooled and expanded, other forces stepped back into smaller roles. The strong force kept nuclei intact. Electromagnetism prepared electrons for future atoms. The weak force faded into the background. Gravity remained, guiding the future. Even though stars would not shine for hundreds of millions of years, gravity was already building the places where they would be born. The night sky we know, with its patterns and colors and marvels, was a promise gravity made in silence. And now, as we follow that promise forward, we approach a turning point. The fog will lift. Light will finally escape. Darkness, true darkness, will fall for the first time. Then, gravity's seeds will wait in the quiet for fire. So our journey continues, toward the moment when the universe becomes transparent, and the cosmos reveals its first image to itself. Now we drift gently into Part 10. Part 10. The Universe. Still too young for stars to the eye, those early seconds would have looked empty. No galaxies, no planets, nothing recognizable. But emptiness is never truly empty. In the darkness, the blueprint of everything was quietly forming. This was a universe in transition, no longer a blinding plasma, not yet a place where light could travel. Gravity was gathering matter in whispers. The strong force had formed protons and neutrons. The weak force had set their balance. Electromagnetism waited patiently for the moment when atoms could exist. And yet, there was nothing to see. This era, between a few seconds and a few million years old, was a quiet suspension between chaos and creation. A place where time stretched, cooling continued, and the cosmic story prepared for its next transformation. Everywhere, hydrogen and helium nuclei drifted free, constantly encountering electrons, yet unable to hold them. The universe was still too hot, still too energetic for atoms to form. Those electrons simply buzzed away, unable to settle, refusing to be bound. Stars were impossible. Planets, a distant dream. Life beyond imagination. But beneath the darkness, gravity was at work more patiently than ever. It slowly gathered matter into gentle clouds, long before any fusion would ignite, pulling the earliest building blocks toward one another with quiet determination. Imagine floating through that young universe. No visible objects, no twinkling stars, no shades or shadows, only a smooth, nearly uniform expanse. And yet in all that stillness, a future galaxy might be forming right beside you, invisible except for a slight density increase. The universe was too young to burn, but not too young to hope. This time is often called the Dark Ages of the Cosmos. A poetic name, though scientifically accurate. No light could travel, so nothing could shine. Photons remained caged within the plasma haze. The cosmos was like a theater before the play begins. The stage is set, the cast assembled, the script ready, but the lights still off. Still, something quiet and extraordinary was unfolding. The universe was learning to structure itself. Gravity deepened the tiny ripples left behind from the earliest moments. Slightly denser regions drew in more matter, forming what would one day become clusters of galaxies, while emptier regions grew emptier still. This process, subtle and invisible, was the foundation of cosmic architecture. It's a strange thought that if the early universe had been perfectly smooth, no ripples, no fluctuations, nothing would ever have formed. No stars, no planets, no you. A flawless cosmos is a lifeless one. Fortunately, perfection was never its intention. In those young millions of years, the cosmos continued expanding. The rate slowed. The temperature fell. Electrons roamed restlessly, waiting for space to become calm enough for them to be captured. Soon, but not yet, atoms would assemble. As the universe cooled, something remarkable began to happen. Radiation lost control. At first, photons dictated everything. Their energy dominated matter, pushing and scattering particles. But as expansion continued, matter became more important. Protons and neutrons, tiny though they were, carried mass, and mass is what gravity needs to build cosmic structure. Gravity was taking command. The universe was entering the age of matter. Even though stars would not appear for hundreds of millions of years, the seeds of those stars had already begun to settle into place within the invisible web of gravity, much of it guided by dark matter. Dark matter makes no light, yet its gravitational pull is immense. It formed the framework that regular matter followed, like iron filings tracing the pattern of a hidden magnet. Where dark matter pooled, hydrogen and helium would one day gather. Where it thinned, cosmic voids would expand, vast spaces emptier than imagination. The universe was stretching out into its grand design. From the outside, if there could have been an outside, this era would appear nearly motionless. But on cosmic scales, everything was shifting, drifting, learning where it belonged. Evolution was silent, creation patient. The Dark Ages were not a pause in the story. They were the story's slow unveiling. Meanwhile, neutrinos continued slipping through everything undisrupted, carrying their ancient memory forward. Photons remained trapped, unable to deliver their message across space. The universe waited for that moment of clarity, when electrons would finally settle and light would run free. It would take about 380,000 years for that to happen. A vast gulf in human imagination, yet a mere dawn in cosmic time. When that moment arrived, atoms formed for the first time. The fog of plasma cleared, light pushed through unobstructed, and the universe finally became transparent. That first light, a soft, warm glow, still fills the cosmos today as the cosmic microwave background, the oldest picture of the universe we have ever seen. It is the backdrop of every star and galaxy, a relic from the moment sight itself was invented. But even after that first light escaped, the night sky stayed dark. There were still no stars, no galaxies, only a thin, nearly silent sea of hydrogen and helium atoms stretched across expanding space. The early universe needed gravity's patience a little longer. Over tens of millions of years, tiny clumps grew larger. Gravity slowly drew in more matter, compressing gas clouds until their centers grew dense. Slowly, inevitably, these clouds warmed under their own weight, not yet enough to ignite, but enough to hint that ignition was inevitable. The blueprint was becoming real. Every star you will ever see, every supernova, every nebula, every sunrise, traces its heritage to this invisible time, a period so subtle that the universe looked empty and yet so profound that everything depended on it. It teaches us a powerful truth. Creation often hides in waiting. Becoming takes time. The universe did not rush its triumphs. It nurtured them in darkness. Millions of years passed, clouds thickened, gravity deepened its pull, pressure rose, temperature climbed, and then, at last, in a universe nearly 2 million years old, the first stars ignited. Darkness was over, light had returned, this time for good. Those first stars were giants, blazing intensely, living fast, dying young. They forged carbon, oxygen, iron, the elements of planets and life, and seeded them into space with explosive brilliance. But all of that wonder, the glittering sky, the warmth of suns, the promise of life, was born in the slow work of an empty age. The universe was too young for stars until it wasn't. And with that transformation, a new question softly rises. What will those first stars make, and how will their fires change the dark into a canvas for galaxies? Now we drift ahead toward the moment starlight finally breaks the cosmic night. We move into Part 11. Part 11. Matter and antimatter, a cosmic imbalance. The early universe should have created matter and antimatter in equal amounts, and they should have destroyed each other completely. Yet, a tiny imbalance occurred. For every billion pairs that vanished, one extra particle of matter survived. We exist because of this cosmic asymmetry. In the first microseconds after the Big Bang, creation and destruction were indistinguishable. Particles appeared from pure energy, electrons and positrons, protons and antiprotons, perfect counterparts, identical except for the sign of their electric charge. Every piece of matter had a mirror opposite, and when opposites met, they annihilated into light. If the universe had followed that balance perfectly, nothing we know would exist. No stars, no planets, no atoms, no life. Only radiation would fill the void, an empty universe, bright but barren. But nature made a tiny mistake, or perhaps a tiny choice. For some reason we are still trying to understand, matter gained the faintest advantage, one extra particle for every billion eliminated. Such an imbalance might seem insignificant, a numerical rounding error, but that fraction saved creation. That tiny surplus became everything that would endure. We are built from the fortunate leftovers of annihilation. Imagine that time. The universe was a tempest of collisions, a furnace so hot that matter and antimatter flickered into existence only to vanish again in the heartbeat of a photon. Energy transformed into particles, particles transformed back into energy. The process repeated endlessly, but always left behind the faintest trace of matter. Somewhere in that storm, the symmetry broke, and that broken symmetry became the reason anything remains. Physicists call the mystery baryon asymmetry, the question of why matter was favored over antimatter. There are hints, possibilities woven into the laws of physics, but no final answer. Was it a quirk of quantum fluctuations? A subtle imperfection in the weak nuclear force? A condition hidden within the energy of the early universe? Whatever the cause, it happened quickly, in less than a millionth of a second, and the result was permanent. The universe would never again be a perfect balance. Matter had been given the smallest advantage, and time would multiply that victory across eternity. As the cosmos expanded and cooled, the window for transferring energy into matter slammed shut. Eventually, the heat dropped too low to spontaneously create new particles. What was left, the survivors of the annihilation, became the foundation for everything we see today. Those survivors are ancient in a way nothing else can be. The hydrogen in your veins is older than the first stars. The protons in every atom of your body are relics of the first second. We are built from particles that won history's first battle. The early universe could finally move forward. Without annihilation overwhelming creation, protons and neutrons persisted long enough to fuse into the first atomic nuclei. This marked the beginning of chemistry, the moment when matter had a stable form to protect itself from the chaos still raging around it. Hydrogen and helium, simple but indestructible, rose from the ashes of annihilation. Even now, the traces of antimatter linger as a cautionary echo. In the heart of stars and in the collisions inside particle accelerators, when matter and antimatter meet, they still erase one another perfectly, releasing pure energy in return. The universe remembers what it took to survive. It carries the memory of what it nearly became, a place where every attempt at form was instantly undone. This delicate imbalance also holds a quiet philosophical wonder. Why should existence triumph over emptiness? Why should matter be allowed to persist? We cannot say whether the imbalance was luck or a fundamental truth, but the cosmos seems to prefer becoming rather than remaining void. Even the smallest tilt away from symmetry is enough to create worlds, enough to allow complexity to rise, enough to permit consciousness to wonder about itself. In the earliest ages, the leftover matter was still wildly sparse. For every photon, every particle of light, only a billionth of a matter particle existed. Light dominated everything. Matter was humble, hidden, waiting. But gravity is patient, and eventually, matter's small advantage became a universe. Those few remaining particles gathered over millions of years. The tiniest clumps grew into immense clouds. Clouds collapsed into stars. Stars forged the heavier elements, carbon, oxygen, iron, everything that makes planets solid and life alive. Every breath you take is possible because so much annihilated. Every memory you hold is a triumph over symmetry. You are built from the universe's stubborn refusal to vanish. There's something beautiful in that. We are not just shaped by survival, we are made of it. Even today, the slight imbalance remains written across the cosmos. The universe contains matter, galaxies full of stars, but almost no antimatter in sight. Wherever astronomers look, they see the same story. Matter won everywhere. The victory was decisive, but the margin was razor thin. And so, when we admire the night sky, we are really gazing at the aftermath of the universe's earliest miracle. The moment existence tipped the scales, the moment all future possibilities were spared from oblivion. This cosmic imbalance was not a paradox, it was a beginning. Now, as matter spreads farther apart with the expansion of space, as galaxies drift like lanterns on a dark sea, the same question quietly follows. How did this leftover matter transform into the first sources of light? How did the universe learn to illuminate itself again after all the brilliance had collapsed into darkness? To answer that, we journey forward toward the birth of atoms, the release of light, and the awakening of visibility. Now we drift into Part 12. Part 12. Cooling without sound. As the seconds passed, the universe expanded and cooled like breath fading in winter air. There was no medium for sound to travel through, no air, no vibration. Every change happened silently, without a single ripple of noise. Silence in the deepest sense, not as the absence of activity, but as a consequence of it. The cosmos was too hot, too diffuse, too strange for air or anything resembling atmosphere. Sound requires matter to pass along a vibration, molecules nudging neighbors. But in the early universe, matter was not yet organized enough to carry that message. Creation unfolded in perfect quiet. The universe cooled because space itself was stretching. It was not heat leaking into a colder void. There was no outside for it to escape into. Instead, as space expanded, the energy that once filled a smaller cosmos was now spread over a larger one. Temperature is a measure of how much energy exists in a given space, so as space grew, heat faded. This cooling was gentle, but unstoppable. The beginning of thermodynamic destiny, every fraction of a second brought the universe into a new phase, new conditions, new rules, new possibilities. In the first moments after the Big Bang, everything was expanding too quickly for structure to appear. But now, the pace was slowing enough that matter could begin to hold itself together. Gravity tugged at particles, pulling them toward denser regions. Forces separated into their modern forms. Light tried to move but was trapped in a fog too dense to pass through. Even so, the direction of change was clear. Order was creeping into chaos. Structure was emerging from fire. It is easy to picture noise when imagining a universe in transformation. Crackling fire, thunderous explosions, colossal impacts. But the actual story was quieter than quiet. The very nature of the environment prevented vibration. No rumble accompanied the cooling. No roar marked the birth of hydrogen or helium. The first atoms whispered into existence without a sound. In that silence, the universe learned stability. As expansion continued, electrons slowed their frantic dance. They remained free, at least for now, but their motions were no longer wild enough to tear apart every structure that tried to form. When protons and neutrons fused into light nuclei, deuterium and helium, that too happened silently. Even nuclear fire was muted. There were no crackling sparks, no screams of matter being born, only a smooth shift in energy from one form into another. Silence is often seen as emptiness, but the silence of the early universe was full of motion, full of transformation, full of potential. During these silent seconds and minutes, the universe's fate was being written at every scale. Physics was laying ground rules that would shape everything to come. The strong force sealed atomic hearts. Electromagnetism would one day bind electrons in orbit. Gravity was preparing space to gather. The weak force made transformations possible. Light waited for its future freedom. Each force learned its role in stillness. Silence made clarity possible. If we fast forward from the first minute to the first few years, cooling remained the universe's constant task. Expansion continued. The temperature dropped from billions of degrees to millions, then to thousands. But even as warmth faded, the universe remained uncomfortably hot, a blistering ocean of charged particles. Still no stars, still no planets, still no sound. The reason is simple. Atoms were not yet complete. A complete atom needs an electron bound to a nucleus, but electrons were still too energetic, breaking free every time they tried to settle. The universe needed to cool another 100,000 years before their calm would be enough to hold shape. Though particles collided constantly, nothing solidified into visible form. Matter was waiting for temperature to fall low enough for peace. Meanwhile, space grew. Distances stretched, the fog thinned. The cosmic pressure dropped, allowing memory to accumulate. Ripples of denser matter deepened under gravity's pull. This is how galaxies begin, not with flashes, but with a whisper. The silence of cooling was not passive, it was creative. Each moment of cooling brought more complexity. First quarks, then protons and neutrons, then nuclei, soon atoms, eventually molecules, later stars and planets, finally life, all from silence. Imagine standing, or simply existing, at that time. Around you stretches an endless universe of brilliant opacity, a featureless glow in every direction, nothing to hear, nothing to see, and yet everything in motion. Behind the glowing fog, gravity pulled at the threads, weaving the first network of structure. Neutrinos streamed through the cosmos, carrying away ancient information. Even photons, still trapped, grew less energetic as the universe expanded, their wavelength stretching, their heat reducing, their influence dwindling. Cooling was the universe's heartbeat. It has not stopped. Even now, the cosmos continues to cool. The glow from that primordial plasma, released when atoms finally formed around 380,000 years after the Big Bang, is now stretched into microwaves, chilled to just 2.7 degrees above absolute zero. The universe has become a quiet place, and yet its silence is the record of every moment that ever happened. The cooling of the universe gave us history. It gave us direction. It gave us time. If the universe had stayed hot, expansion could not create distance fast enough to let energy dissipate. Atoms would never hold. Stars would never form. Life would remain a dream locked in plasma. Cooling is the reason existence did not vanish. Through silence, the cosmos preserved its chance to become something more. This silent transformation teaches us that not all creation announces itself with a sound. Sometimes the most important changes are slow and quiet. Sometimes the universe grows not with explosions, but with stillness. As the temperature dropped further, the day would come when electrons finally joined protons in lasting embrace, when the fog lifted and light burst forward unhindered into space. Darkness would finally arrive, real darkness, and then stars would awaken to end it once again. So we continue into that cooling story, toward the moment the universe becomes visible for the first time. The silence is not over. It carries us to the birth of transparency, to the release of light, and to the first glimpse of a cosmos ready to shine. Now we drift gently into Part 13. Part 13. The first elements are forged. Within minutes, hydrogen and helium nuclei began to form, the two simplest elements. Everything heavier, carbon in your cells, oxygen in your lungs, iron in your blood, would require the fires of stars still far in the future. These first minutes of cosmic life were unlike anything that would ever come again. The universe, still glowing with unbearable heat, was now finally cool enough for protons and neutrons to bond into something more enduring. The chaos that once tore everything apart was losing its strength. Something gentle and miraculous was beginning. This era is known as Big Bang nucleosynthesis, the first forge, the earliest chemistry, the moment when matter began to write the periodic table. But it was a short window, a cosmic heartbeat lasting only about 20 minutes. After that, the universe expanded and cooled so much that fusion became impossible until the birth of stars hundreds of millions of years later. In that brief window, the universe made almost all the hydrogen and helium that will ever exist, the simplest ingredients, the foundation of everything else. Hydrogen, one proton, one electron waiting in the future, would become the fuel of stars. Helium, two protons and two neutrons at its heart, would become their first creation. The universe also forged tiny traces of deuterium, a heavier hydrogen with a neutron added, helium-3, and lithium. These rare isotopes are still found today, quietly reminding us of that ancient furnace. All other elements, carbon, nitrogen, oxygen, iron, would need a different kind of fire, a different kind of pressure, a different kind of death. Stars would one day offer their cores as crucibles. Supernovae would one day scatter heavier elements into space. But that future had not yet arrived. Right now, the cosmos was just learning how to build. Fusion began as the universe cooled below 1 billion degrees, still vastly hotter than the center of the sun, but cool enough that protons and neutrons could stick together without immediately being ripped apart by stray photons. The strong nuclear force took hold, pulling particles close and binding them tightly. Imagine that moment at a microscopic scale, protons and neutrons drifting through a fiery ocean, searching for partners, collisions, separations. Then, a bond that doesn't break. A nucleus is born. For every durable connection, countless attempts failed. Fusion was not easy. But success came often enough to change the universe forever. In these first moments, hydrogen dominated, and for good reason. It requires no neutrons, no pairing, no additional partners to exist. A proton on its own is a complete hydrogen nucleus. Simplicity wins when time is short. Helium, on the other hand, needed a careful assembly. 2 protons, 2 neutrons dancing into alignment, locking into harmony. Helium-4, as it's known, is one of the most stable nuclei in existence. Once formed, it almost never splits apart. The universe found in this nucleus a kind of peace, a configuration that simply works. Roughly 25% of all matter, by mass, became helium during these minutes. Most of the rest remained hydrogen. That ratio would shape the entire future of cosmic evolution. The more helium stars would one day inherit, the faster and brighter they would burn. Every fraction of a second, new nuclei formed. Every moment, the universe changed. But the universe was also expanding relentlessly. Heat continued to fall. The space between particles stretched. Collisions grew rarer. The forging slowed like embers cooling after the flame's wildest flare. Eventually, fusion stopped altogether. The universe was still not stable enough for atoms to form. Electrons remained free, repelled by the heat. But the hearts of atoms were ready. Their futures were already waiting in the silence between collisions. In this newly forged chemistry, the story of stars was encoded in advance. Hydrogen would fuel them. Helium would give them structure. Lithium would gather only in trace amounts, a mystery astronomers still study today. That moment, when the first elements locked into place, is when the universe became capable of complexity. With hydrogen and helium, gravity could form great clouds. With clouds, stars could ignite. With stars, heavier elements could be born. With heavier elements, planets could assemble. With planets, chemistry could thrive. With chemistry, life could emerge. And with life, the universe could finally understand itself. All of that potential began here, in the first minutes, in silence, in invisible light. Hydrogen and helium may seem simple, but simplicity is the seed of wonder. Water, air, bone, breath, all would trace their origins to these first elements. When you look up at the night sky, every star you see is made mostly of hydrogen, the ancient gift of those early minutes. The air you breathe, the DNA inside you, the planet beneath you, all are built upon the foundation established in this era. The cosmos wrote its first vocabulary using only 2 letters, H and He, and from that sparse alphabet it eventually composed galaxies of meaning. The first elements symbolize something more than just chemistry. They represent the universe's desire to become more than energy alone, to become form, structure, and story. And so, nucleosynthesis ended, but its products endured. The young universe entered a new and longer phase. Continued cooling, growing darkness, the slow work of gravity shaping raw ingredients into the promise of stars. At this stage, the cosmos was still opaque, the fog of plasma still blocking light's escape. Nothing could yet be seen. But the first chapter of matter was complete. Taking a cosmic breath, the universe held its creations close and waited for the next transformation. The next great shift, the birth of atoms, would require time, patience, silence. Hundreds of thousands of years later, electrons would finally calm enough to join these nuclei. Photons would break free. Light would, for the first time, truly shine. Everything that came after, every star, every galaxy, every heartbeat, depended entirely on these first fragile bonds between protons and neutrons. Sometimes creation needs only a few ingredients and a willingness to wait. Now, our journey moves forward into the moment when the universe, at last, becomes transparent. We drift into Part 14. Part 14. Space becomes transparent. Hundreds of thousands of years later, electrons finally settled into orbit around nuclei, letting light travel freely for the first time. The universe became transparent, a single moment forever frozen as the cosmic microwave glow we detect today. For so long, the cosmos had been filled with a blinding radiance that no eye could see. Photons were everywhere, but none could travel far before colliding with a free electron and scattering like headlights in a dense fog. Light existed, but sight did not. Then, around 380,000 years after the Big Bang, temperature fell to about 3,000 degrees Celsius, cool enough for electrons to calm and attach themselves to the nuclei that had waited so patiently. This union, the birth of neutral atoms, was called recombination. Electrons joined protons and helium nuclei, and in doing so, they cleared the fog. The moment electrons settled down, photons were suddenly free. They stretched their wings and began a journey through the expanding universe, a journey that continues even now. The universe, once opaque like the inside of a star, became clear. From this point on, light could travel. The cosmos could finally be seen. That first light still exists. It has never stopped traveling. Its glow, now stretched into microwave wavelengths by the expanding universe, washes over us constantly. We call it the cosmic microwave background, CMB, the oldest image of the universe. It is a photograph taken when the cosmos was a child, a portrait of its earliest visible moment. If you look up at the sky with the right instruments, that ancient glow is everywhere, uniform, peaceful, nearly smooth, with tiny ripples that trace the seeds of galaxies yet to form. Those faint ripples, differences of only one part in 100,000, are the fingerprints of history. They reveal where matter gathered more strongly than average, where gravity would one day form stars and clusters. From a soft glow of near perfection, the blueprint of all structure emerged. Imagine the scene. A universe newly transparent, soft warmth filling every direction, hydrogen and helium drifting gently in space, gravity quietly sculpting the future. There were still no stars, no planets, no color, no shapes, no visible objects, only a serene fog thinning into a cosmic dawn. And yet, light had arrived. This transition marks one of the most important moments in cosmic evolution. Before recombination, the universe was a symphony without a listener, energy, motion, structure forming unseen. After recombination, the universe acquired witnesses, photons that could remember the journey. The CMB is memory made visible. It tells us how hot the universe once was, how it expanded, how matter was distributed, what shape the cosmos would take. Every satellite that maps this glow, COBE, WMAP, Planck, helps humanity look back almost to the beginning. We cannot see earlier, not with light. Before this moment, the universe denied photons any chance of travel. Earlier chapters are hidden behind a veil, only neutrinos and gravitational waves have crossed. But from recombination onward, the universe preserves its own story in light. The temperature of this ancient glow has fallen drastically over billions of years. Once as hot as a furnace, this radiation has cooled to just 2.725 degrees above absolute zero. A cold whisper of creation. It is everywhere, gently filling all of space. It is the oldest light you will ever see, a cosmic lullaby still singing across the void. As transparency emerged, darkness followed. Not darkness from lack of light, but from distance. The first stars did not yet exist, so although photons could now travel freely, there were no bright objects to illuminate the night. The cosmos entered a long, deep night, the cosmic dark ages, lasting hundreds of millions of years. During this time, gravity continued gathering matter into clouds, cold hydrogen pooled into deeper wells, darkness hid the quiet work of creation. This stage of cosmic evolution is mysterious and profound. No telescope has yet fully captured the dark ages. They remain a hidden chapter between the first light and the first stars. But we can sense what was happening. The transparency of space allowed structure to grow, and the structure leads inevitably to fire. In the densest clouds of primordial hydrogen, pressure slowly increased. Gravity squeezed the gas tighter and tighter until temperatures at the cores soared once again. Stars began to form. The first stars, massive and brilliant, far larger than our sun. They lived brief, dazzling lives and died in violent supernovae. forging the heavier elements the universe so desperately needed. Thus, transparency, the release of light, led to darkness, and darkness prepared the stage for the return of true starlight, the birth of atoms, the release of photons, the emergence of clear space. These were not just changes in physics, they were invitations to history. From this moment forward, the universe would evolve not just physically, but visually. What once hid beneath the diffusion of plasma now revealed itself to light and to possibility. Everything we explore in astronomy, every distant galaxy, every nebula, every exoplanet, every sunrise and comet, depends upon transparency. Without recombination, space would never have cleared. Light would never have escaped. We would never have seen stars form or galaxies spin or universes expand. The cosmos became a place that could be observed. It became self-illuminating. And so, when you hear the phrase transparent universe, think of it not just as a physical transition, but as the universe taking its first breath as something visible and knowable. In that glow, we see not only where we came from, but why the world has structure, why stars burn, why galaxies exist at all. It is the quiet moment when the universe opened its eyes. That ancient light, soft, uniform, and eternal, still touches you now. Every second, countless photons from that first morning pass through your skin. The universe remembers its childhood, and it shares that memory with you. As the glow faded into night and stars waited to ignite, the stage was fully set. Everything that would ever shine had been given the means to be seen. And now, another question rises like starlight approaching the horizon. What happens when the first stars blaze into existence, ending the darkness for good? We follow the light forward, into Part 15. Part 15, From Chaos to Cosmos. In one cosmic heartbeat, the universe had changed from a featureless explosion into a place where structure could grow. Laws had settled, forces had taken form, matter endured, the chaos had found order, and the universe had found its rhythm. It is almost impossible to grasp how quickly everything transformed. In less than a second, energy became matter. In minutes, the first elements formed. In hundreds of thousands of years, space turned transparent and light was finally free. The universe began as a roar, a flash of pure existence, and almost immediately began learning how to be a place rather than a moment. With each passing stage, the firestorm calmed. What was once unthinkably violent became merely hot. What was once impossibly small became vast. The young cosmos was no longer a chaotic burst, but a system guided by logic, shaped by laws that would never again be rewritten. Through trial and transition, the universe chose permanence. The rules we take for granted, gravity pulling downward, atoms holding together, light traveling in straight lines, crystallized into reality during those first moments. Before then, physics itself was fluid, able to shift, uncertain of its final form. But now, structure could thrive. The universe had become a cosmos, a word that means order, beauty, arrangement. Chaos did not vanish, but it became a tool rather than the story. There is a quiet poetry in that. Order does not destroy chaos, it tames it. Inside every star that would one day ignite, chaos would fuel light. Inside every living cell, chaotic molecules would form the foundations of life. Within every mind yet to evolve, electrical storms would create thought and memory. Chaos became the engine behind complexity. From disorder, harmony emerged. After transparency arrived, the universe slipped into darkness again. A peaceful dark, a creative dark. The dark ages were not a void, they were a nursery. Hydrogen and helium, the gentle children of nucleosynthesis, drifted through a cooling void, waiting for gravity to shape them. And gravity did not rush. It gathered matter grain by grain, atom by atom, forming clouds so immense they stretched light years across. These clouds, invisible but growing dense, were the first hints of structure. The early cosmos was beginning to think architecturally. Each cloud was a seed. Each seed was a star in preparation, and the first stars, would change everything. But transformation at this scale requires patience. Millions of years would pass before the first star ignited, hundreds of millions before galaxies took form, billions before planets orbited in quiet lanes of dust. Cosmic time is slow, but never stagnant. During those long ages of darkness, the universe rehearsed the future. Gravity deepened wells of matter, dark matter sculpted hidden frameworks, gas cooled and condensed, forming the first proto-galaxies. Yet no one could see it, not even light itself. The cosmic microwave background still glowed, but dimly, stretched by expansion, fading into the dark. Until stars were born, that was the only illumination. Still, it was enough to reveal that the universe was no longer simply expanding, it was evolving. The difference is profound. Expansion is motion, evolution is intention. The cosmos had begun shaping itself. Even the smallest density fluctuations, tiny imperfections left behind from inflation, were now growing under gravity's patience. Those imperfections would one day become enormous galaxy clusters, each containing hundreds of billions of stars. Every galaxy that would gleam in the night sky, Milky Way included, began as a ripple in the fabric of space-time. A ripple so faint, so slight, that without it, the universe would remain empty. Imperfection was destiny. If the early universe had been perfectly smooth, it might have been beautiful, but hopeless. Nothing could cling, nothing could gather, nothing could be. But the universe was not perfect, it was precise. A balance of smooth and uneven, just enough randomness for creativity, just enough structure for stability. The cosmos was young, but it was clever. It had learned to grow from its own imbalance. As time slowly moved forward, the invisible clouds continued contracting. Pressure built, temperatures rose. Once again, not everywhere, but in special places where matter concentrated most. These would become the first stars, giants dozens of times more massive than our sun, burning fiercely with blue-white brilliance. When they ignited, they sent light into the darkness for the first time. The universe, which had been dark since transparency, would shine again. The cosmic rhythm was fully established, expansion and cooling followed by gathering and ignition. Creation had cycles, patterns, music. From the fire of the Big Bang to the cradle of gravity, the universe transformed chaos into cadence. And while this journey continued for billions of years, galaxies spinning into existence, stars living and dying in cycles, the rules remained unchanged. The forces that took shape in the first second continued to govern everything, everywhere. Even you, the atoms inside you still obey those same laws. The quarks inside your protons still feel the same strong force. The electrons around your atoms still dance to electromagnetism. Your body is held to the earth by the same gravity that once guided hydrogen into the first stars. You are the universe playing by the rules it learned long before stars existed. Everything that would ever be alive depends on the fact that the universe once cooled enough to allow stability and once warmed enough to allow ignition. We live in the perfect middle, between fire and ice, between chaos and order, between destruction and creation. From those early transformations, a grand narrative emerged, the story of structure, light, chemistry, life, and consciousness. And though we occupy only a tiny chapter in that story, we are rooted in its beginning. When we look back at the Big Bang, we are not watching something foreign. We are watching our own deepest origin. The hydrogen that fuels the stars, the helium that makes them shine, the elements forged in their cores, the planets cooled from their dust, the water that gathers in oceans, the cells that divide and remember, the neurons that spark a thought. Every one of them is a continuation of the same unfolding. The chaos has truly become a cosmos, a place where the universe can not only exist but understand itself. And now, floating in the calm that comes after creation, finds rhythm. A gentle question arises. What will the cosmos become next? The next stage of our journey lies just beyond the first light, where stars ignite, galaxies form, and the universe takes on the beauty we see today. For now, we drift forward with wonder, into what comes after the beginning. As the universe expanded, cooled, and learned to build, it carried us in its quiet momentum. From the first quarks to the first light, from unthinkable chaos to the harmony of stars, every moment has shaped the world that now holds you gently in its care. The cosmos has been patient. It waited billions of years so that atoms could become oceans, and oceans could become life, and life could dream of the